we propose an image-based AI framework to predict effective properties of composites, trained on simulation data and applied directly to real SEM images. First, statistical volume elements of the composite are generated, followed by thermal conductivity simulations. To generate the statistical volume element, the following information is required. First, the morphology of the fillers is defined. Next, the filler size distribution is specified. Finally, the filler volume fraction is assigned. By combining these inputs, a wide range of statistical volume elements can be generated. Next, thermal conductivity simulations are performed on the generated SVEs. As illustrated here, appropriate boundary conditions are applied to compute the thermal conductivity of each SVE. The simulations are conducted along the 6 principal heat flow directions. The resulting thermal conductivities are used as ground truth labels for constructing the simulation-derived database. Using the generated SVEs, 2-dimensional images are created for image-based learning. The SVE is rotated about its principal axes to generate multiple 2-dimensional views. Although the SVE remains the same, different rotation angles produce different views, which are used for data augmentation. However, a clear visual gap exists between simulated images and real SEM images. To bridge this gap, the simulated images are first pre-processed, and CycleGAN is then used for domain adaptation. As a result, the simulated images are transformed to closely resemble real SEM images while preserving their microstructural geometry. From the generated images, both local and global features are extracted for property prediction. We first extract local features by defining regions of interest within the image. The image is divided into 3 regions: filler, interfiller, and matrix. For each region, both spatial coordinates and class labels are assigned to construct a structured database. Next, global features are extracted using an autoencoder. The image is compressed into a low-dimensional latent vector, which captures the overall structural characteristics. Now, I will introduce the multi-input CNN used for property prediction, followed by the prediction results. Here, we use a multi-input CNN to predict material properties. The network integrates full images, ROI images, ROI coordinates, ROI class labels, and a latent vector. These features are fused into a unified representation for prediction. This figure shows the results on unseen validation data, achieving a high accuracy with an R² of 0.93. Here we prepare real SEM images for model prediction. The original SEM image is cropped into patches with the same size as the training data. Each patch is treated as an independent input, enabling direct application of the trained model to real SEM images. Finally, we validate the framework using real SEM images. Predictions from multiple independently trained models are compared with the experimentally measured bulk thermal conductivity. As shown, the predicted mean values closely match the measured bulk value of 0.420 watts per meter Kelvin. This demonstrates that the proposed framework can reliably predict bulk thermal properties directly from real SEM images. Thank you for attention.